welcome to the first lesson of the second module, which is on analysis of strain. In the first module, we have discussed about the analysis of stresses and we have seen various aspects of stresses. Now we are going to discuss certain aspects of strain in this particular lesson. Now it is expected that after completing this particular lesson, one will be able to understand the concept of axial strain, the concept of normal strain, and strain at a point in a stressed body. One will be able to understand the relationship between stress and strain, which is very important when we talk about the strength of materials. It is not only the stresses, but the relationship between the stress and the strain is important. One will be able to understand the concept of modulus of elasticity, which we need for the analysis as we go along. As the scope of this particular lesson includes, we look into certain aspects which we have discussed in the previous lesson through the question answer sessions. The questions which we posed last time we will discuss in this particular lesson before we proceed forward. We will evaluate the normal strain and strain at a point. We will look into the relationship between the stress and strain, and thereby the Hooke's law, which is required or which is defined for the elastic body, and then the different terms which we get in the stress strain relationship and the modulus of elasticity. As we said that before we start looking into the aspects of the strain, let us look into the questions which we had posed last time. The first question posed was, what are the equations of equilibrium in Cartesian coordinate system in a stressed body? Well, the equations of equilibrium in Cartesian coordinate system, they are del sigma s del x plus del tau x y del y plus x equals to 0, and del tau x y del x plus del sigma y del y plus y equals to 0, where x and y are the body force components. Now as you know that sigma x and sigma y are the normal stresses in the x and y direction, and tau xy is the shearing stress component. So these two defines the equations of equilibrium in a two-dimensional system. The second question posed was, what are the equations of equilibrium in polar coordinate system of a stressed body? Now the equations of equilibrium in polar coordinate system, this particular aspect was discussed in the 6th lesson of the module 1, wherein we had defined the stress component, the radial stress sigma r, the circumferential stress sigma theta, and we had seen how to derive these equations of equilibrium. The radial direction stress is sigma r, the circumferential stress is sigma theta, and consequently we have the shearing stress components which are tau r theta. And in a polar coordinate form, these are the equations of equilibrium: del sigma r del r plus 1 by r del tau r theta del theta plus sigma r minus sigma theta by r is equals to 0, and del tau r theta del r plus del sigma theta del theta upon r plus 1 by r tau r theta equals to 0. These are the two equations which defines the equations of equilibrium in polar coordinate system for a two-dimensional stress analysis. The third question which was given was what is the value of maximum shear stress if sigma 1 is equals to 10 MPa and sigma 2 is equals to 0. Let us look into, if you remember, the Mohr circle of stress in which we had the sigma axis and the tau axis. Now, in the Mohr circle, the point on the maximum normal stress is sigma 1 and the minimum normal stress is sigma 2. Now, the radius of this circle defines the maximum value of the shearing stress, which is tau max, and tau max is given by sigma 1 minus sigma 2 by 2, and in the given problem sigma 2 is 0 and sigma 1 is 10, thereby maximum shearing stress is 10 by 2 as 5 MPa. So, these are the three questions which are posed, and the answer for this are as defined. Now, having looked into these aspects of the stresses, now let us look forward, let us look into certain aspects of the strain analysis. Now, we are going to look into the aspects of axial or the normal strain. Now, let us assume that we have a body which is acted on by force P. The length of the body let us assume as L. Now, when a body is subjected to either change in the temperature or subjected to the forces, it undergoes deformation. And in strength of materials, we are interested to look into this deformation, and we try to define a quantity in terms of this deformation. Let us assume that after deformation, the length is L plus delta. Thereby, delta is the deformation or the extension of the body. Now, we define a quantity which is the ratio of this deformation to the original length and is generally designated as epsilon as equals to delta by L, and this is known as strain. The load, the force which is acting in the body is in the axial direction, and we assume that the deformation is uniform at any point along the length of the body, and thereby everywhere the strain is same. Also, as we have looked into earlier, that a body when it is subjected to an axial force, we get a stress which we call as normal stress, which is the stress normal to the cross section of the body. In line with that, we define that the strain or the deformation which is along the axis has the axial strain, and since to compare with the normal stress, we call this strain as the normal strain. So, strain associated with normal stress is called as the normal strain, and we define this as elongation per unit length. Now, as this is the ratio of two lengths, basically this is a dimensionless number quantity, and thereby there are no units as such. However, it is customary to define strain in terms of the ratio of the lengths. Let us say it is meter by meter or millimeter by millimeter for a body, and accordingly sometimes we say the units of the strain as millimeter by millimeter, and this strain is defined in terms of a number. Sometimes we define this in terms of percentage as well. Now, the strain when we are calculating for the deformation, the delta, we are assuming that there is uniform deformation in the entire length of the bar. If the deformation is not uniform, if we compute the strain from delta by L, we are assuming the strain on an average sense over the entire body. Now, if the strain is not, the deformation is not same everywhere, if the deformation varies along the length of the bar, then the way we had computed the stress at a point in a stressed body, we compute the strain also at a point in a stressed body. Let us look into this particular figure where a bar which is fixed at one end is subjected to a pull, say P. Now, let us assume that we are interested to find out the strain at a point within this body. Let us say this is A, which is at a distance of x from the fixed end. Now, to evaluate the strain at a point in a stressed body, what we do is we consider an imaginary fiber, let us say A B, which is of length dx or delta x. Now, this bar, when it is subjected to pull P, the fiber also is stretched or deforms, and let us assume that this is the stretched fiber which was originally delta x. Let us say this is A dashed B dashed, and the length of this stretched fiber is delta x plus delta del delta. Thereby, extension of this fiber is del delta, and as we have defined, the strain epsilon for this particular fiber is del delta over del x, and this strain at this particular point A we can define as strain as equals to, as delta x tends to 0, this is del delta over del x. This we can write as d delta over dx. Hence, d delta is equals to epsilon dx. So, over the length L, if this is the length of the member which is defined as L, then over the entire length the deformation delta, which is integral 0 to L d delta, this is equals to integral 0 to L epsilon dx, and this is the deformation if the strain varies along the length of the bar. If we have uniform strain everywhere, then this is equals to epsilon integral 0 to L dx, which is L, and epsilon we get as delta by L, as we have seen earlier. If the strain is constant everywhere, it is uniform, we get delta by L. If it is not, then delta is integral 0 to L epsilon dx. And that is how we compute the strain at a point. Now, in strength of materials, we have seen that how to calculate the stress at any point in a stressed body, and we have seen various components of the stresses. Now, we have defined a quantity which we call as strain, strain at a point, or strain on an average sense if it is uniform over the length of the bar. Now, what we need to do, which is of relevance in strength of materials, is the relationship between the stress and the strain. Now, for evaluating the relationship between the stress and the strain, we take a body, apply a tensile pull in the body, and we apply this load gradually over the bar. For each increment of the load, we try to find out how much deformation the body undergoes. So here if you look, here this is a bar in which we have formed the section in a different cross sectional form. This part is called as the grip, which is inserted in a tensile testing equipment, and the whole bar is pulled. Now on this bar we fix up a length which is in between this bar, which is little away from this grip, so that the length on which we focus our attention is not affected by the variation of the load in the grip zone. And this length on which we focus our attention, we call this as gauge length. So this is the initial distance between two predefined points, and these we call as gauge length. And as I said, this length we consider in between the bar and little away from the grip zone, so that this particular zone is not affected by the force distribution or the stress distribution in the grip zone. Now if we apply a pull on this bar gradually, as we have seen, the bar will undergo deformation, thereby there will be a change in the gauge length, and if we measure that increment or the deformation, then we can compute the strain. And as we have seen earlier, the stress for a body which is subjected to an axial pull, the normal stress is the axial pull divided by the cross sectional area. So for each increment of the load, we can compute the stress, we can compute correspondingly the strain, and then we can plot a curve to establish the relationship between the stress and the strain. Now if we look into the plot between the stress and the strain, the plot is something like this. In this particular figure, this axis represents strain and the y axis represents stress. Now for each increment of the load, we compute the deformation, and thereby we get the strain, and for several such points we plot it on a steel bar, and this is the profile which we get at different stages of loading. Now in this particular figure, if we look into that, there are various terms indicated into it. One we have called as proportional limit, this we have called as elastic limit, this particular point we have called as yield point, this is the ultimate strength or the ultimate stress, this particular point, actually this is wrong, this is not normal, this should be nominal. This is the nominal failure strength. Now here, if you note it, that we compute the stresses here with reference to the original cross section of the bar which we had computed. As you can visualize that when we are pulling this bar, when we are applying a tensile pull, as it deforms, the cross sectional area of the bar will reduce. Now the stress, as we know, is load divided by the cross sectional area. The cross sectional area we always take as the original cross sectional area, and accordingly we get this profile of the curve. If we take the actual area, load divided by the actual area, then the stress value will be different from this. In fact, from this particular point we will have a configuration something like this. Now the stress, when we compute with reference to the original cross sectional area of the bar, we call those stresses as the nominal stresses, and correspondingly the nominal strain. Otherwise, if we compute the stresses with reference to the changed cross section of the bar, we call that stress as the true stress and the corresponding strain as the true strain. So here what we have plotted is the nominal stress and the strain. Now the meaning of this proportional limit is, up to the level of proportional limit, the stress is proportional to the strain. So we say the stress sigma is proportional to the strain epsilon. Now this particular point, elastic limit, is the point up to which, if the load is applied on the body and if it is released, the body comes back to its original state, and that is what we call as the elastic limit of the body. But beyond elastic limit, if we apply the load, if we go beyond elastic limit and if we release the load, the specimen does not come back to its original state, and some amount of deformation is permanently set within the body, and that is what we call as permanent set. And yield point is the point when the body starts yielding. It goes beyond the elastic limit, the plasticity start forming into the section, and if we keep on applying load at that particular point of time, in fact without increasing in the load, the bar deforms, the extension, the deformation becomes excessive, and it reaches to a stress which we call as the maximum stress, and there is a loading down on the load when the bar fails, and that is how we get a failure stress which is lower than the ultimate stress. So this is the maximum possible stress that a bar can attain, which we call as the ultimate stress, and this particular point is the failure stress. Now in the bar, these 2 points, this proportionality limit and the elastic limit, virtually is very difficult to distinguish, and we consider that up to this level, up to the elastic limit, the stress is proportional to the strain. And if we remove this proportionality constant, sigma is written as a constant times E, which is constant for that material, and this is what is known as the Hooke's law. So up to a proportionality limit or up to the elastic limit, the stress is proportional to the strain, or stress is equals to E times the strain, where E is called as the constant of proportionality or the modulus of elasticity, which is an important parameter in our strength of materials. It is called as modulus of elasticity, and this is constant for the particular material which we are considering for evaluating the stress and the strain, and this is known as Hooke's law. The stress within elastic limit, the stress is proportional to the strain, or sigma is equals to E times epsilon. So we have seen then the Hooke's law, which is up to the proportionality limit, the stress is proportional to the strain, and thereby we get sigma is equals to E times epsilon. We have seen the elastic limit, as I said, that if the bar is loaded and it is allowed to extend, if the bar is within elastic limit, if we release the load, the bar is expected to come back to its original state. The permanent set, as I have defined, that as the member yields, it reaches to the yield stress, then the plasticity forms in the section. Then if we release the load, as we have seen in case of elastic material, when the bar is still within its elastic limit, the bar comes back to its original position, but once it starts yielding, then if we release the load, the bar does not come back to its original position, and some amount of deformation gets permanently set in the body, and that is what we call as permanent set. Yield point, again, as we have seen, is the point where the material starts yielding or it goes beyond the elastic limit, and the plasticity starts setting in the member. Well, these are some of the stress strain relationship for different material. If we take a concrete specimen, apply a tensile pull in a tensile testing equipment, then we will get a profile similar to this, which is the stress strain relationship for concrete. If we take material like aluminum, cast iron or high carbon steel, we get this kind of profile, and these are necessary to know the relationship between the stress and strain and thereby the modulus of elasticity, so that we can compute the stress, we can compute the strain, and we can establish the relationship between the stress and the strain in a body when the material is used either for some equipments in the machine parts or in a structural body where we are interested to evaluate the stress and the strain. We need to know the relationship between the stress and the strain of the material with which that particular machine part or the structure is composed of. Now, as you have seen in the previous figure, in the first figure, in this particular figure, as you have seen that we have a defined yield point. In this particular zone, this particular curve shows that we have a defined yield point. So, corresponding to this particular stress, we know that this is the yield stress, which we define as sigma y. But as we have seen in the subsequent figure, that we do not have any defined yield point, and in strength of material, when we deal with the stresses within elastic limit, we need to know what is the value of the yield stress beyond which the member will start yielding. So, we try to limit our stress when we deal with elastic level of analysis. We like to limit our stress up to the elastic level. So, we need to know what is the value of the yield stress, but from this kind of stress strain distribution, it is difficult to know what is the value of yield stress. Now, to compute the value of yield stress, what we do, it is observed that the strain corresponding to the yield stress value is of the order of 0.2%, which is 0.002. 0.002 is the strain. Now, if we draw a tangent to the curve at this particular point, which we call as initial tangent, and if we draw a line at 0.2% strain, if we draw a line parallel to this initial tangent, the point where it cuts the curve, the stress strain curve, the corresponding stress we called as the yield stress, and this yield stress normally we designate as proof stress. So, for the material where we apply a tensile pull and plot a stress strain curve, and corresponding to that particular stress strain curve, if we do not get a defined yield point corresponding to which we are interested to evaluate the yield stress, then we compute the yield stress in an indirect way corresponding to 0.2% strain offset, and this stress we call as proof stress or the yield stress of that particular material. Well, as we have seen earlier, in case of the stresses, when a bar is subjected to axial pull, we have computed the stress which we have defined as the normal stress, the stress which is normal to the cross section of the bar, and the load is acting perpendicular to the cross section through the axis of the bar. Now, for an axially loaded bar, if we are interested to compute the strain, let us assume that this particular bar say is fixed at this end, the length of this bar is L and subjected to a pull P. Thereby, if delta is the extension, then the strain is equals to delta by L, and we consider that this particular bar or this analysis which we carry out is within the elastic limit of the bar, and as we have seen right now in the stress strain relationship that within the elastic limit of the bar the stress is proportional to the strain, and we can write sigma is equals to E times epsilon. So, in place of epsilon we can write this as E times delta by L. Hence, from this expression we can write the deformation delta is equals to sigma times L by E. And as we know that this is a bar which is axially loaded, the load is acting through the axis of the bar at any cross section, the normal stress sigma is equals to P divided by the cross sectional area. So, sigma is equals to P divided by A. So, if we substitute the value of sigma in this, we get delta as equals to P L by AE. So, for an axially loaded bar, we know the axial, if we know the axial pull, if we know the cross sectional area, if we know the length, and if we know the material with which this bar is made of, for which we know the modulus of elasticity, then we can compute what will be the deformation in the bar, considering that everywhere the strain is same. However, if the strain is not same everywhere, if there is variation of the strain as we have seen in the previous calculation, that strain or the deformation delta, as we have seen that deformation delta is equals to integral 0 to L epsilon dx, and we have seen that from our stress strain relationship sigma is equals to E times epsilon. So, this is equals to integral 0 to L. In place of epsilon, if we write this is sigma by E dx, and sigma if we write as P by A, then we have delta as equals to integral 0 to L P by A E dx. Now, if P cross sectional area they are different, then we will get deformation different at different points. But if the axial load P and cross sectional area A they remain same, there is no change, then we get the same expression which is equals to P by AE. If P by AE is constant, then integral dx will give you L. So, delta is equals to PL by AE for a constant value of P and cross sectional area A. However, if there is variation on P and A along the length of the bar, then we get different deformations at different point, and correspondingly the strain value will be different, and that is how we compute the deformation in an axially loaded bar. Now, having defined this strain, we have looked into the concept of stress in the module 1. Now, we have defined the quantity which we call as strain, we have established the relationship between the stress and strain, and within elastic limit we have seen that in an axially loaded bar how we can evaluate the deformation if we know the load. If strain is uniform, then what is the relationship between the deformation and the corresponding load with the cross sectional area of the member, and in terms of modulus of elasticity of the material. And if there is a variation of the load, if there is variation in the cross sectional area, then it is expected that deformation is going to be different, and accordingly the strain will be different at different points. Now we come back to the example which I had given you last time. This is related to, in fact, to the evaluation of the stresses at different points. Now this is a truss member in which are supporting a billboard. The billboard is supported on this. There are two trusses, and the cross sectional area of all the members, let us call this as this point as A, this point as B, this as C, this as D, and this as E. Now we are interested to know the stress in each member when this particular board will be subjected to a load on its area, and the load has been converted here. The forces are acting as 3 kilonewton here and 6 kilonewton here. So what we need to do is to evaluate first the forces in each member, and once we can compute the forces in each member, then since the members are pin jointed, we will have the axial forces in each member, and this axial force divided by the cross sectional area will give us the stress, and that is what we are interested in, to calculate the stress in each member. Now from this triangular configuration, this distance is 6 meter, this is given as 4 meter, this is given as 4 meter. So distance BC is also going to be equals to this divided by this equals to 4 divided by 8, which is half. So this is 3 meters. So if we call this as theta, then if we take the free body of this part, if we take a section here, then we have the member which is like this is theta, and we have the horizontal force acting here which is 3 kilonewton. Now let us say the direction of this force is this, and the direction of the force here is in this direction. Now if we take the horizontal component of this force, which is FAC, so FAC sin theta is equals to 3 kilonewton. FAC sin theta is equals to 3 kilonewton. Now sin theta from this is equals to 3 by 5. This is 4, this is 3, so this length is going to be equals to 5. So sin theta is equals to 3 by 5. So FAC is equals to 5 kilonewton. If we take the vertical equilibrium of the forces, so FAC cos theta, and if we call this force as FAB, then FAC cos theta is equals to FB, or FAC cos theta minus FAB is equals to 0. That is the vertical equilibrium. So FAB is equals to FAC cos theta, and value of cos theta is 4 by 5, and FAC being 5, so the value of FAB is 4 kilonewton. Now if we look into the direction of the forces as we have assumed over here, this is the force in the joint, so the member is subjected to a force like this, which is a compressive in nature. So the member AC will be subjected to a compressive force. member AB, in the joint we have a force direction in this. So, in the member the force is in this direction, and thereby the member AB is under tension, and this is a tensile force. So, member AC and member AB is subjected to a force of 5 kilonewton and 4 kilonewton. So, this divided by the cross sectional area, 5 kilonewton divided by 100 millimeter square will give us the stress in FAC, and correspondingly 4 kilonewton divided by 100 millimeter square will give me the stress in FAB. Likewise, we will have to compute the forces in this bar, in this bar, in this bar, and in this bar. Now, supposing if we cut the structure from here and take the free body of the upper part of it, then we get a configuration which is like this. Here we have 3 kilonewton, here we have 6 kilonewton. This is member force, let us call that as FBD, because this is A, this is B, this is C, and this point we have called that as D, and this point we have called as Z. So, this is FBD, we have a member in this direction which is FCD, and we have force FCE. We can compute the forces. If we take the moment of all the forces with respect to this, then 3 kilonewton is going to contribute a moment 3 times this distance, and FBD will have a moment this times this distance, which is equals to 3. So, 3 kilonewton multiplied by 4 is a clockwise moment. If we take the moment about C as equals to 0, so 3 times 4 is equals to FBD times 3. So, this is anti-clockwise moment. So, FBD is thereby equals to 4 kilonewton. And again, this is at the joint, it is in this direction. So, in the member the force will be in this particular direction. So, this gives us again a tensile pull. So, this is a tensile force. So, this force divided by the cross sectional area will give me the stress in the member. Now, this particular angle we had assumed as theta, hence this is also theta, and again we can take the horizontal and the vertical equilibrium of these forces, of all the forces, and we can compute the value of FCE and FCD, and thereby the value of FCD we will get as equals to 5 kilonewton, and this is a tensile pull, and the force FCE will get as 10 kilonewton, which is a compressive force. And so, we have seen AB, AC, BD, CD, CE, and the member which is remaining is BC. If we take the equilibrium of this particular joint, we have a 6 kilonewton force here. This is joint B. We have member AB, we have member BD, and we have member BC, for which the force will be FBC, and the value of FBC from this will come as 6 kilonewton. And which is a compressive force. So, once we get the forces in each of these member, the force divided by the cross sectional area will give me the stresses in each member, and that is how we compute the stresses in the member. Now, by stating that the truss joints are pinned, it means that the forces which are getting transmitted in each of the members are purely axial forces in nature. Now, having discussed that particular problem, which was related to the evaluation of the stress, as we had discussed in the previous module, how to compute stresses at a point in a stressed body. Now, in this particular lesson, we have seen how to compute the deformation in a member for an axially loaded member, or if there is variation in the loads or the cross-sectional area, what is going to be the deformation in the member along the length of the member. Now, let us look into some of the examples that how do you compute this deformation if the forces in the member is known, if we know the cross-sectional area of the member, and if we know the material property, which is the modulus of elasticity of the material. Now, in this example, we have a steel rod which is having a cross-sectional area of 300 millimeter square, and the length of the bar is 150 meter. It is suspended vertically from one end. The rod supports a tensile load of 20 kilonewton at the free end. We will have to find out the elongation of the rod, or we will have to find out first the deformation. The value of E is given as 2 into 10 to the power 5 MPa. So, it is like you have a bar of length 150 meter, and it is supported at one end, it is hung from the top, and at this free end this bar is subjected to a load of 20 kilonewton. The length is 150 meter. So, we are interested to compute that what is going to be the elongation of the bar. This bar, because of the axial pull, the bar is going to be stretched, it is going to deform. So, we are interested to find out how much deformation this bar will undergo because of the axial pull which is acting. One end is fixed, other end is being pulled. Now, here as we have seen, the deformation delta is equals to PL divided by AE, where P is the axial pull acting in the bar, L is the length of the bar, A is the cross-sectional area of the member which is uniform here, and E is the modulus of elasticity of the material. So, this is equals to P is given as 20 kilonewton. So, 20 times 10 to the power 3 Newton. L is 150 meter. So, 150 into 10 to the power 3, so much of millimeter, divided by cross-sectional area A, which is 300 millimeter square, multiplied by E, which is 2 into 10 to the power 5, which is Newton per millimeter square, megapascal. So, this 10 to the power 3, 10 to the power 3, 10 to the power 6 cancels out with 10 to the power 5 and 0, 10 to the power 6. This 0 2 cancels, this 2 gets cancelled. So, we have 53 times 150, so this is 50. So, this is equals to 50 millimeter. So, this is the amount of elongation that this particular bar will be undergoing because of this load. Let us look into another example problem, and this is interesting because here we have a bar, an elastic bar, the bar is within the elastic limit, and in this we have variable cross section. The bar cross section is not uniform as in the previous case. Here for this particular stretch of the bar we have one cross sectional area. Let us call this as A, this is B, this is C, this is D. Now, part AB, the segment AB is having area of 1000 millimeter square, segment BC is having 2000 millimeter square, and segment CD is of 1000 millimeter square. And this particular bar is subjected to a pull here of 200 kilonewton, here it is 400 kilonewton, here it is 100 kilonewton, and here it is 100 kilonewton. Now, for such kind of system, we need to look into that whether the whole bar is in equilibrium under the action of these forces or not. If we look into the bar is subjected to the action of an axial force of 400 kilonewton in the positive x direction, and in the negative x direction we have 100 plus 100 plus 200, so 400. So, this is in equilibrium. Now, if we take the free body of the different parts of this particular bar, then we can find out that what is the amount of forces that each segment is subjected to. Now, let us take a section somewhere here. Let us call section 1-1, and if we take the free body of this particular segment is subjected to a pull here 200 kilonewton, and as we have seen the free body in our module 1, the opposing force also will be 200 kilonewton. So, this particular segment is subjected to a pull of 200 kilonewton. If we take a section here, section 2-2, and if we take the free body part of it, then here we have a force 200 kilonewton, here we have a force which is 400 kilonewton acting in the other direction. So, the resulting force we have 200 kilonewton acting on the opposite direction, so it has to be balanced. So, this has to be 200 kilonewton. So, this is being pulled, it has a compressive force of 200 kilonewton, and if we look into if we take a free body at this part, then we have the free body part as like this, this is 200, this is 400, and this is 100. So, 100 plus 200, 300 on this side, 400 on this side. So, it has to be balanced by 100 on this side. So, this particular segment then is subjected to 100 here, 100 here, which is under compression. So, the first part, this part is under tensile pull of 200 kilonewton, the central part is under compression of 200 kilonewton, the third segment is under compression of 100 kilonewton. Now, for this, if we compute, if we calculate the deformation for 3 segments, we can find out the total delta as summation of PL by AE, as in each of these 3 segments the cross sectional area over this stretch, over this particular stretch the cross sectional area remains same, over this particular segment the cross sectional area is same, over this segment the cross sectional area is the same. So, we have we can write this as equals to, for the segment AB, as say P1 L1 by A1E plus P2 L2 by A2E plus P3 L3 by A3E for 3 segments. Now, for the second segment, this P2 is negative, is compressive, if we call P1 as a tensile as positive. For the third segment, P3 is compressive and again negative. Now, if we compute, if we substitute these values, as we know the value of P, we know the value of L1, we know the value of A1, and correspondingly P2, L2 and A2, we know the values of P3, L3 and A3, and if we calculate that, we can compute the value of the deformation, and this delta is equals to 200 into 10 to the power 3 into 2000 divided by 1000 times 2 into 10 to the power 5. Second one will be minus, which is equals to again 200 into 10 to the power 3 minus is we have 100 into 10 to the power 3 into 1000 divided by 1000 times 2 into 10 to the power 5, and if you compute this, this is going to be equals to 1 millimeter. Now, I have another problem for you, which is an aluminum bar with a cross sectional area of 160 millimeter square carries the axial loads. You compute the value of the deformation. I am going to discuss this particular problem in the next class. Now, to summarize, now this particular lesson included the concept of strain at a point and axial and normal strain, the stress strain relationship and the relevance of difference point in the stress strain curve, the example to demonstrate how to evaluate the strain and thereby the deformation in a stressed body. Now, I have some questions for you to set which you will have to answer. I am going to discuss these questions in the next class. Now, what is meant by elastic limit? What is the difference between nominal stress and true stress? How will you evaluate strain in a bar with gradually varying cross section? And answers to these questions will be discussed in the next class. Thank you very much for your attention. Welcome to the second lesson on the course of strength of materials, in which we are going to discuss today on the analysis of strain, part 2. And in the last lesson we have introduced the strain after discussing the different aspects of stresses in module 1. Now, in this particular lesson, it is expected that once it is completed, one should be able to understand the concept of axial and the normal strain in a stressed body of variable cross section. In the last lesson, we have discussed about the strain, the axial strain, the normal strain in a bar which is of uniform cross section. In this particular lesson, we are going to discuss that if a bar is of variable cross section, then what will be the strain in that particular body. To understand the concept of shearing strain, also one should be able to understand the concept of shear modulus and Poisson's ratio. As the scope of this particular lesson includes the recapitulation of the previous lesson. In the lesson what we have discussed in the first one, we will look into it through the question of system of stresses, and also we will look into how to evaluate the stresses at different points. This particular lesson includes the recapitulation of the lessons which we have discussed already, evaluation of stresses in polar coordinate system,